we have understood lens formula, lens maker's formula, and when would we get a converging lens and when would we get a diverging lens. Now let's have a situation in which we're combining two thin lenses by very small distance. As in, when I say very small distance, it's not that they are separated away, they're just kept side by side. So I'll not draw any diagrams for you because that would needlessly confuse you. So I'll have lens 1 here and a lens 2 here. So this thing, this could be convexo-concave, biconvex, biconcave. And this thing over here is also a lens, concavo-convex, biconvex, or doubly concave, whatever. If I combine them, I mean they're touching. I should rather say two lenses in contact. So when you have two lenses in contact, I can use the same underlying logic that lens 1 would refract my rays of light and produce an image. That image would be an intermediate image because I also have a lens 2 to further refract the rays, which means lens 2 would give rise to a new image, the final image. So if I apply my lens formula to lens 1, L1, what I would get is 1 by V1 minus 1 by U is equal to 1 by F1. This F1 guy over here is giving you the focal length of lens 1. Similarly, this thing here now is acting as an intermediate image or rather the object for lens 2. So for that I can use 1 by V final image due to this L2. That's 1 by V1 is equal to 1 by F2. This is the focal length of lens 2. If you add them up, this thing and this thing would go away. So you'll be left out with 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. Now this essentially becomes the formula for two lenses in contact or combination of lenses in contact with each other. Now what happens over here is, I know that lens formula is 1 by V minus 1 by U is equal to 1 by F, which means I can further replace this combination of lenses L1, L2 with 1L of focal length F if that is equal to this relation. You get it? I guess it's very clear. In place of this, I'll have 1 by F. So 1 by F is equal to this quantity. So L has F as focal length, L2 has F2, L1 has F1, and I can replace this two lenses in contact combination with one equivalent lens. So this is a resultant focal length of the lenses in contact. Now there's a new thing which you should be aware of, that this was combination of lenses. Let's say I need to find out the focal length for different kind of shapes. How would I use my lens maker's formula? This is just a digression from here because you will gradually understand what I'm getting into. So let's say you have the lens maker's formula as 1 by F is equal to mu 2. The reason I'm doing this is, if you don't know how to calculate F, how can you write these equations? How would you write these equations? So you need to know how to write F, how to calculate the value of F. See, the thing is, I would not try to take things linearly in this chapter, because as I have told you before also, I have to make this chapter interesting and non-boring. So I have to take the liberty of jumping back and forth between topics. Now this thing is 1 by R1 . Now this R1 and R2 is dependent on geometry, right? And I'll have to change my F because of that. What all possibilities do you have? The simple case of biconvex with equal radii. Simply R, R. Very easy. Put the values. What you would get is mu2 by mu1 minus 1. This is positive R. This is negative. So negative, negative is positive. So 2 by R. So this is for your biconvex lens. Let's say you have a biconcave lens. And even these two would have similar R values. The catch over here is to understand that these R values would be positive in this and negative in this. Let's try to understand that. This would give you mu2 by mu1. This is negative. This is positive. See, this is positive facing. So negative, positive is negative. So again, a negative thing, right? So this becomes negative thing. This is minus 2 by R. See, these are magnitudes essentially. These are not with sign conventions. So I'll have to use sign conventions later words. Now similarly, I could have something like a plano convex lens. Now the catch here, all the discussion here was for this thing only, plano convex. Why? The moment you have a plano convex thing, this is your regular R, value is known to you. What about plano? The idea is, if you try to increase the radius, the curvature starts becoming like this. So if a flat surface given to you, the radius of curvature is infinity, or not defined, or too large. This is your infinite value. Just write over infinity. So what I will do is, in place of R1, I'll simply put minus infinity, and this would vanish away as 0, and rest all same. Now if I give you plano concave also, it would be not difficult for you, right? Or rather, convexo concave also would not be difficult for you. Just need to understand what values have to be substituted over here, and you could get F as positive or negative. Now let's try to come to a situation as in, how do we denote F in a way which reduces my calculation or analysis extension. So there's a term called power of lens. Reason why power of lens is studied is because I have to carry this all throughout, 1 by F, 1 by F, and it's not easy to carry through reciprocals all the time. So I defined something called power as inverse of focal length. And if I'm following SI systems, focal length is essentially in terms of meters. So this would be 1 by meter. So power has meter inverse as the dimension, or if you want to write a dimensional formula, it's L to the power minus 1, and the SI unit or the name is diopters. And the symbol is simply capital D, right? So which means if you have a focal length of 20 centimeter. For positive, I'll first convert it to meters, and then your power would be equal to 1 by f, which is 1 by 0.2, which is 5 diopters. Now I can change this in terms of power. 1 by f is your effective power. This is equal to P1, power of your first lens, plus power of your second lens. So I have converted my focal length relation to power values. P is equal to P1 plus P2. This makes more sense, easier to remember. That's why you're trying to convert the focal length thing to power of lens. Now, I have talked about only biconvex, biconcave and plano-convex. All the other diagrams would have a similar treatment. Just do a similar calculation for this and you'll understand it through. I'll just help you with this plano-convex thing. Now, your 1 by f over here would be equal to, for simplicity, let's say mu of the medium is some 2, right? And outside you have vacuum. So 1, so you'll have 2 upon 1 minus 1, and let's take r as 50 centimeters. Okay, so this would give you 1 by r1. r1 is the infinity, that to minus infinity, minus 1 by, this is to the negative side, right? So minus 50 centimeters. So 1 by f is equal to, this is your 2 minus 1, so 1, and this is your 0, this is your 1 by 50. And as I have taken everything in centimeters, this gives you 50 centimeters. Let's convert it to meters. That would be 0.5 meters. So your power would be simply 1 by f. F should be in meters. That would be 1 by 0.5. That would be your 2 diopters. I mean, this wraps up your idea of 2 lenses in contact, or rather 2 thin lenses in contact. This would be your formula for the focal length combination or the power formula. Power is simply P1 plus P2, and focal length would be inverse of your effective, is the summation of the individual focal lengths. So we have understood, if 2 thin lenses are in contact, the resultant power would be P1 plus P2, or the focal length relation is 1 by f is equal to 1 by f1 plus 1 by f2. I'll read it for you. 1 by f resultant is equal to 1 by f1 plus 1 by f2. This can be also written as P1 plus P2 is equal to P. But this is for lenses in contact. What about lenses not in contact, separated by a small distance? To understand what happens when you have kept the lenses at some distance away from each other, we need a small reduction on deviation produced by lens. Let's understand that first. Let's say you have biconvex lens. See, it's easier to draw biconvex lens, that's why we keep on using biconvex lens, but it's not that it is done only in the case of biconvex lens. You could take a doubly concave lens or rather a biconcave lens, and do the same things, and it would give you the mathematical result to be the same. Now, this is the principal axis. An object kept over here, would produce some kind of an image here, because I have taken the assumption of a converging lens. I have a real image formation. This is your O, this is your I. Now over here, the ray was actually headed towards this direction. But now it is going in this direction. So this is the delta produced, or rather the deviation produced. Just write deviation by the lens. Now, how would I find the value of this deviation? It's actually very easy. Let's say this ray intersected H above the principal axis. Okay, let this angle be alpha, this angle be beta. In this triangle, the bigger triangle, just write a point over here, something like an X. So in the triangle, just write it over here. In triangle OXB, I can safely say that delta is equal to alpha plus beta, property of triangle. So delta, or the deviation, is, and as we are talking about paraxial rays and small aperture and all that, I can approximate alpha and beta as tan alpha and tan beta. So this would essentially be equal to tan of alpha plus tan of beta. This symbol is approximately, rather almost equal to. Tan alpha is equal to H upon this value, right? So let this be some P. P again is the optical center. So this thing becomes H by PO plus H by PI. Let's write in terms of object distance and image distance. Now image distance will be positive to the right, but this will be negative. So this would give you H upon minus U plus H upon V. This is your delta. Now what I need is, what would be delta? I know from lens formula that 1 by V minus 1 by U is equal to 1 by F. Let's focus over here. If you focus over here, I can take H common. Let's take H common. So delta would be essentially equal to H 1 by V minus 1 by U. Does this make sense? I hope it's actually very clear. I don't have to explain every bit of it. If I use this thing over here, what I would get is H upon F, because 1 by V minus 1 by is equal to 1 by F. So I'll just write 1 by F for this. So delta comes out to be H upon F. So remember this, deviation produced by a lens is dependent on where exactly that ray is hitting the lens or meeting the lens, that H corresponding to that point, upon the focal length of the lens, H upon F. Now this forms the basis. You would be wondering, why do we need this? But this actually forms the basis when two lenses are kept small distance or are separated by small distance. I'll just write that thing for you. Two lenses. I'll start a new thing. Two lenses apart by small separation. Now you'll understand why I have done this for you. There's a logic behind that. Let's say you have one lens here. And the other one here. Now, if a parallel, I'm taking parallel because it's easier to deal with a parallel ray. It comes over here. Now, it will be getting refracted by some amount. Reach here. And after reaching here also, it will be getting refracted further. Finally fall here. Right? Now, if I produce this forward, this should have been the path of my unrefracted ray, but this is my final ray. So this is your delta, or the actual deviation produced by these two lenses. What about this angle? This angle is your delta 1 produced by this L1. Similarly, for L2, if you extend this forward, this would be your delta 2. So even this is your delta 2. Right? So if you note this thing down, you'll understand that delta can be found out in terms of delta 1 and delta 2. Why? If I redraw this triangle, let's redraw it for you. This guy is delta, this guy is delta 1, and this guy is delta 2. So obviously, delta is equal to delta 1 plus delta 2. I have drawn this triangle over here. Now, I need to find what happens when these two lenses are separated by small distance. Let that distance be D. I know that if this is parallel ray and meeting at this point, this actually is the resultant focus. Right? From where? The measurement has to be done from this point. Why? Why this point? Because if I take this backward, the deviation is thought of from this point. See, think it through. Pause the video, think geometry of the situation, understand that if I keep a lens over here and a parallel ray comes over here and then intersects this point, this is acting as your focal length, resultant focal length, and this is your F is your focus point, and I can think of a lens situated over here. This is a lens. Dotted denotes your resultant lens which would be there. Now that's the need of your delta over here. That is what I'm interested in, delta. Let's say this is H1. So even this thing is H1. But this thing, what about this? This would be H2, right? Now, what exactly is delta 1? Use this logic. Your delta 1 would be equal to H1 by F1. Delta 2 would be equal to H2 by F2. Finally, what would be delta? Delta would be equal to H1 by resultant F, right? This is your resultant F, this length over here. And I also know that delta is equal to delta 1 plus delta 2, which means your H upon F is equal to, rather this is H1, right? So right H1 over here. H1 upon F1 plus H2 upon F2. Now I need to get rid of this H1, H2, H. So how would I do that? It's actually very easy. First understand this, that H2 can be written in terms of D2, this D. How? And now in this situation, this thing is H1, this thing is H2, right? If you want to redraw this, what we'll understand is, here you have H1 and till here you have H2. So this is H1, this is H2. So this essentially becomes H1 minus H2. Now if this thing is H1 minus H2, this H1 minus H2, if it is a bigger triangle, this triangle, what you would get is, this guy is D, this guy is H1 minus H2, and this angle over here, delta 1. This is your delta 1. So, by all logic, this upon D is your tan delta 1. So, H1 minus H2 upon D gives you tan delta 1. Now, if this angle is small, I can approximate this as just delta 1. So, your H1 minus H2 becomes D times delta 1. What exactly is delta 1? This is your delta 1, H1 by F1. This is H1 by F1. So in place of H2, I can simply write H1 minus D H1 upon F1. Let's just use this thing. Let's just use this thing from here onto here. Right? Let's use this. What we left out with is H1 upon F is equal to H1 by F1 plus H2 by F2. H2 is this quantity. So first H1 by F2. Now next thing is minus dH1 by F1. So minus dH1 by F1 by F2. So minus dH1 by F1 by F2. So another thing comes out. This H1, H1, H1 and H1 can be cancelled out. So 1 by F is equal to 1 by F1 plus 1 by F2 minus D f1 f2. This is your formula for two thin lenses separated by a small distance, or two lenses apart by a small distance, is 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2, where d is the separation between them, f1 f2 is the product of focal lengths. I can convert this thing into power relation too. Power is equal to P1 plus P2 minus D P1 P2. Makes sense, proper sense. I just inverted the power thing and found out the power relation too. Now, what exactly is the value for your focal, rather the location of the lens? This is your location of the lens, this much, from the second lens, this measurement. If you go for the measurement of this value, this is essentially, let's draw the smaller triangle here which you have. The smaller triangle is this one. This guy is the thing which we are interested in, right? This angle is your delta, and this angle is your, sorry, this side is your h1 minus h2. This is what we are after, x. So this x over here would be simply h1 minus h2 by tan delta, and if you approximate this, this would be equal to h1 minus h2 by delta, because the angles are small. So what exactly is x? I know the delta value is h1 by f, right? And I also now know a lot about h2, h1 values also. So I'll simply use h1 minus h2 from here, dh1 by f1. And delta is how much? h1 by f. So if you use this guy from here and this guy from here and put both the things into here, your x would come out to be d of f upon f1, and this is the location for your resultant lens or effective lens. So this length is your df upon f1. See, this f thing is your resultant f, which have been calculated from this equation.